ready.
Thank you so much for the introduction. So hello, I am Vanessa Kwong. I'm currently a fourth year studying biology and physics. My research is on optical characterization of two-dimensional heterostructures. My advisor is Dr. Andrew Zhou from the Department of Physics and Astronomy. So condensed matter research has been largely relevant in the development of transistors and photodetectors. And of this research, there's a large focus on 2D materials, which have unique tunability to discover quantum phenomena by either stacking or twisting them to create devices that we can optically evaluate. So of the 2D materials, I focus on TMDs, specifically WSe₂, because when exfoliated to a monolayer, there's an electron in the valence band that could directly jump to the conduction band without the assistance of a photon. And so this pair, which is the excitation, emits a photon once excited. And then the process of my research is to first stack exfoliate flakes from bulk materials to create electronically tunable 2D devices, and then optically characterize them by taking PL and absorption spectra. And the application of this is to create novel valleytronic devices, which the TMDs could be twisted to a moiré superlattice. For example, this could be used for discovering new correlated states. In this paper shown on the right, they used twisted bilayer graphene at the magic angle to observe the behavior of a correlated insulator. And my method of device fabrication is to first place a single piece of bulk material onto Scotch tape and then fold the tape until you create a thin array of the material that you decide to exfoliate. So right here, there is an array of HBN on the tape. And then that array is then placed onto a silicon oxide wafer chip, pressed down, and so the flakes will transfer on. And once evaluating flakes, we could use to build this device shown down here, where the HBN is used as substrates around the WSe₂ TMD layer in the middle. And then exfoliated graphite could be used as either top gate or contact, where the top gate encapsulates the entire device, and the contact makes contact with the TMD, and also the gold leads, which is where you would apply a voltage to manipulate excitons. And here are some of the samples that could be used for the device. On the top left is a thin or relatively thin and larger flake of graphite, which could be used as top gate. Bottom left is a HBN around 20 to 40 nanometers, and then top right is a TMD, specifically WSe₂, which is a monolayer. And all of these flakes could be used because they're uniform, and we could check for the thicknesses depending on its contrast with the silicon oxide wafer chip against the microscope, and also by using AFM or atomic force microscopy. And then at the bottom, I have a rough outline of the design of the device that I made, where the gold leads are already pre-patterned onto the silicon oxide wafer chip by electron beam evaporation. And then here is the contact and top gate piece, which touch the gold leads, and then HBN on the outside, and the middle yellow is the TMD or WSe₂. And then here is an image of the transfer stage setup. So we have the objectives where you manipulate the zoom and focus. And then there's a heated stage where you place the chip with the samples you want to transfer, and also the eventual pre-patterned gold leads where you want to drop off your heterostructure on. And then on the right side is a glass slide attached by vacuum where we have PDMS and PC, which is water soluble, so that when you drop off the entire device, we heat and cool it down so that it anneals and gives us this finished product, which has the PC residue. And because it's water soluble, we could use chloroform and isopropanol to wash it all off to give us our clean and finished device. And so from that image of the device, we could kind of see the outline of the TMD, the WSe₂ here. Although it's not right in the middle of the two HBN substrate layers, it is still in the device, so we can still optically characterize it by taking a PL spectra. And with this, we shine a supercontinuum laser positioned at this red circle right onto the TMD so that the corners of the HBN match up. And that gives us a curve that looks like this. Correlating back to a figure shown earlier, we have the electron excitation at around 633 nanometers, right where the intensity increases a bit. And then at the larger peak is the photon emission at 750 nanometers. So we could tell that the energy is around 1240 and that we are exciting above the band gap. We could also do an absorption spectra where the peaks could tell us what wavelength of light is absorbed while the others are mostly reflected. So to do this, we shine white light onto the same exact TMD spot where we have the signal as shown in the blue curve. The reference is just by shining the white light onto a single monolayer of WSe₂, which we get the red curve, and then the background is basically where the environment in the device where the TMD is. So in this case, it's between the top gate graphite and also the HBN. So we find another spot where it's only the top gate graphite and HBN. Just take that without the TMD and we get the pink curve, which is the background. And so from that 3 plots of data, we could calculate the actual signal, which we take away the background data and see the difference between the actual signal and the reference. And this down and up behavior is called photoresonance, which is due to background interference and resonance scattering. This is because when white light is shined onto the WSe₂, light is reflected off the wave, causing a phase offset for the different wavelength values. And we can see that the middle of this behavior is also around 750 nanometers, matching up with the PL spectra, also at 750 nanometers, meaning that the TMD has exciton behavior. So to conclude, although this is still an emerging research, we could continue by measuring the same PL and absorbance data of the same device at cryogenic temperatures by placing it in a cryostat and taking the spectras, or also swap out the TMDs for other WSe₂ and MoSe₂, or also stack multiple TMDs within the device to create moiré superlattices when twisted. And with both of those scenarios, we should see different interlayer exciton behaviors. So thank you. These are the references and some acknowledgements for my research. This is my PI, Dr. Andrew Zhou, and I also use the transfer stage from Dr. Louis' lab, and the rest are for the theory support. Thank you.
Okay, great. Yeah, thank you. Okay, so all right, so time for any question and comments from the audience.